Hi, welcome to our video on polar coordinates, it's really great because Cartesian coordinates, although we don't, I guess, refer to them very much in that way, the Cartesian coordinates, let me write that out, Cartesian coordinates, are what we often use as we are taught how to deal with a plane in class. And this is based on the idea in school that, and beyond, I guess, that you can represent the location with two numbers, x and y, or in three dimensions, x, y, z, and so forth. And these two values represent distance. So for example, if I had, going along the x-axis here, 1, 2, 3, and 4, right, this is my x-axis, and then I want to go up 3, so I'm going up to 4, and then here I'm going up 3. We call this location with Cartesian coordinates the point 4 and then up 3, so 4, 3. And that's generally the idea. Well, is there another way to get from the origin to this point? Well, there is, and I'm sure there are many ways that we can think of. Another useful way to think about it is called polar coordinates. What's nice about polar coordinates is that they bring angles into our description of a location. Polar coordinates say, well, how far do you have to go? That's r. And then at what angle do you need to go to get there? And this is fundamentally different from the Cartesian coordinates, because this is saying, well, I'm starting here, how far do I have to go? And at what angle do I have to go to get exactly to this point? And you can get a sense right away that, well, it looks like this is all, like, this is definitely not 90 degrees or 0. It's somewhere in between, maybe close to 40 or 50. But if I go at that angle, at some angle theta, right, from the x-axis, if I go at some angle theta, and I go at some distance r, I can get exactly to that point. And that's the idea of polar coordinates. Now, the way we can deal with this and connect it to Cartesian coordinates is to use a right triangle. We drop that right triangle, and now we have a connection because we have a leg down here, which is 4 units long, that's the x distance, and a leg here, which is 3 units long, which is the height. So we can figure out this r, right? The Pythagorean theorem tells us that a squared plus b squared is c squared. In this case, maybe 4 squared plus 3 squared equals r squared. 4 squared plus 3 squared is 25. That equals r squared. And r equals the square root of that. So r here is just the square root of 25. r is 5. And now we know how far we have to get to this point. We just need to figure out, well, what's this angle over here? And to do that, we can refer back to SOHCAHTOA, our little mnemonic device to remember the basic trig identities, right? The ratio, trig functions, excuse me. And I'm going to use the tangent here. And yes, at this point we could use sine or cosine, but think that tangent might be the most useful, because if we're dealing with Cartesian coordinates, from the start you have this angle and the opposite side and the adjacent side to that angle, which is exactly what tangent uses. TOA, opposite over adjacent. So in this case, the tangent of some angle, theta, equals 3 over 4. How did we figure that out? And this is something you want to definitely cover if you haven't already. I haven't made other videos on this topic, but the inverse tan function, right, tan of -1, that's saying, well, what angle makes 3/4 if you're taking the tangent. So you want to take the inverse tangent of 3 over 4, or it's often written as the arctan of 3 over 4, or perhaps it's written as the arctan of the tangent of theta. And that's, well, the tangent of theta is equal to 3/4. So this is the same thing as the arctan of 3/4, which we've written right here. And these are just different ways of saying the same thing, right? To figure this out in the calculator, you might want to make sure you're in degrees. I've made this mistake way too many times. We're dealing with degrees right now. Make sure you're not stuck in radians, right? You want to be in degrees. So the second tangent of 3 over 4. So you want to hit second tangent and then 3 over 4, or 0.75, and that equals 36.869 degrees. I'll say 36.7 degrees. So I estimate about 50 or so, and that's clearly not accurate. So this is actually about a 36-degree angle measurement. And to write this point in polar coordinates, we wouldn't write 4, 3. We'd say, well, r is the distance, so you have to go a distance of 5 at an angle of 36.87 degrees. And that's the basic idea, but let's even actually step back a little bit more and look at the really general picture here. So we have all the tools we need to convert back and forth between Cartesian coordinates and polar coordinates. So again, here is our plane, and here is a point on the plane. Let me draw this point. This will have some x value and some y value. Well, how can we figure out the r value? It's always going to be the same, right? Because you have to go some distance to get to this point, and you can always find a way to drop a line to form a right triangle. So what's always going to happen is that r over here is going to equal, well, using the Pythagorean theorem, r squared, I'll put our tools over here, r squared will always equal x squared plus y squared. So that gives you a hint. If I give you a point with x and y, you could find r squared by using the Pythagorean theorem. And that's our first tool to convert. The next tool is to think about, well, what does the tangent of theta equal? So if you're given an angle, right, the tangent of theta equals the y side, because theta will be right here, the opposite side, over the x. So this is going to be helpful to convert back and forth between the angle we're given in polar coordinates and into Cartesian coordinates and vice versa. And more specifically, we can get this a little bit neater with x and y. Now, we could solve this equation in terms of y or x. We could say, for example, if I multiply both sides by x, I would get x times the tangent of theta equals y. And then you can also go with, x equals y over the tangent of theta. But we can actually also, it might be friendlier to use sine and cosine in this regard. And I think you'll see why once we write it out. In terms of theta, right, what is the cosine of theta? Let's go back to our acronym. So, COTOA. Well, the cosine is equal to the adjacent over the hypotenuse, which is x over y. Multiply both sides by y, and we get y times the cosine, y times the cosine of theta equals x. So, there we go. No, wait, that does not make any sense. Let me go back, I'm sorry. So, cosine of theta does not equal x over y. What am I saying? Cosine of theta. Well, it's the adjacent over the hypotenuse, that's x over r, right? So cosine of theta equals x over r. Alright, that makes more sense, and this is easier. So, multiply both sides by r, and we get r times the cosine of theta equals x. So we can use r and an angle theta to give us an x value. And what happens if we take the sine of theta? Well, that's going to equal the opposite over the hypotenuse. So that's going to equal y over r. Multiply both sides by r, and we have r times the sine of theta equals y. So now we have all the tools to convert back and forth between Cartesian and polar coordinates, and that's something we'll go over in our next video.